In this video, we're going to talk about using distributional expectations as part of the Great Expectations framework. Distributional expectations provide a way to express relationships that you expect to see in a data set, especially things regarding the shape or distribution of data values in a column or set of columns. To get started, we're going to continue using the data set that we began with from the UC Irvine Machine Learning Repository, their census data set. The data set was constructed with the machine learning task in mind of using or of predicting whether or not an individual is earning greater than $50,000 a year. So I'll pick up sort of where we left off by importing our libraries and setting up the basic processing pipeline that we left off with in the last example. So I'll draw your attention to the fact that we are working with kind of a first batch of this data that we've split out from the original data on their site, which we've further divided into training and testing subsets. Now, let's start off by looking at our data a little bit more closely. Let's take a look at the age column. When we look at this, we see that the data seems to follow what we'd sort of expect for the demographic characteristics of an American workforce. We have individuals from about, looks like as young as 17 years old, and at least one who's still 90 years old. In Great Expectations, we work with our distributional expectations through a concept of a partition. The partition is basically the same histogram that we would use in an exploratory workflow. And what we can do is just build that partition in a way that Great Expectations can use it to test whether new batches from the data set have that same shape. We can construct the partition using a simple utility. And we have a few variants, but first let's take a look at this as, this is a continuous value, the age. And let's go ahead and actually just quickly take a look at what that partition is. So the partition is a set of bins and weights. For each bin, we're defining the range of values that we expect to see, and then the weight just corresponds to how many of the values that we expect in our data set to fall in that range. We can express our expectation in terms of a statistical test. In this case, we'll use the bootstrapped Kolmogorov-Smirnov test, which is a way to compare two continuous distributions to see whether they're the same. Now, it's no surprise that the data set that we just built from will match our expectation at this point. But just to kind of jump ahead of ourselves and show how Great Expectations will work, I'll go ahead and apply that same expectation now to our test data. Now remember that we needed to apply it to our data set itself so that it's a part of our configuration and ready for use in any future batch or delivery of data that we might encounter. But sure enough, our test data seems to follow that same partition of age. Let's do a similar thing looking at the gender column. Now, it's noteworthy here that perhaps quite different from the population at large, in this particular breakdown, we seem to have significantly more women than men present in our data set. Still, we can go ahead and construct an expectation about that. Now, in this case, of course, we're dealing with a categorical rather than a continuous variable. We can go ahead and create a partition. And because this is a categorical variable, we use the chi-squared test in this case. Now, if we look at this, we'll see that for both of these tests, we provide a default p-value of 0.05. You notice that our test is that the value is greater than. That's just a way of saying that we don't expect that we can definitively show the data not to follow the distribution. It's kind of a double negative construction. And not surprisingly, again, on the data from which we constructed it, our expectation is met. Let's do the same. Well, we don't need to look at that yet. Or let's go ahead and look at the same thing we did previously, looking at our test data. And once again, in this case, it seems that we have. You'll notice that the true value of our p-value in that test is not 1 as it was before when there was literally identical, but still we seem to observe the same distribution in our test data as we had in our other data set. Let's go ahead and do another distributional expectation built from the number of years of education, or the highest level of educational attainment that people have. Now we've added these expectations to our configuration object. And at this point, it's straightforward for us to go ahead and save that config. We get our expectations config. We can just take a look at it at the same time here while we're doing that. And what we'll see are many of the standard expectations that are always added, that we expect certain columns to be there. We also see that we've got some expectations that we just added. So our KS test with the partition that we provided, and the same thing for the tests of sex and educational attainment. At this point, let's go ahead and just turn to constructing a model as though we were sort of participating in the UC Irvine's the example format. What I'll do is I'll just build a model using a random forest classifier. And I'll sort of get things ready to process the data for our pipeline, or for our actual machine learning pipeline at this point. And let's go ahead and recall that we had identified what categorical columns we have in this data set earlier. So we're really just kind of taking a lot of shortcuts here to streamline things for our demo. I seem to have been able to type that successfully. And we'll do the same thing now that we've got this function we've got for building a transformer from training data to kind of applying that when we'll want to actually apply our model. So we're exactly just following the same logic again here through. We're just applying those label encoder and one hot encoder that we fit in the previous step. Okay, so now that we've got our defined transformers, let's go ahead and construct and train our model. So we use our first batch of training data, the same data that we have done our exploratory work with. Almost got my typing, or at least some of it. We'll see what other typos I've got embedded there. And then we can go ahead and fit our model. Great. So now we have our random forest classifier, and we can go ahead and test it using our held out data. Again, this is from that same first batch. So our performance is actually really good. That's in line with the high end of what we would expect based on the kind of published results from that data set that's available. So, break out the champagne here. But before we get too excited, let's go ahead and take advantage of great expectations here. Well, the first thing that we can do is make sure that we've applied all the expectations that we had for our training data, just to make sure that our testing data has the same kind of semantic characteristics, the ones that we've at least been able to embed into our expectations. To do that, we can simply call the validate option. And I'm actually going to just do that again and only look at cases where there are unmet expectations. Well, in this case, there aren't any unmet expectations. That's great. Just like we'd expect from data that is sort of randomly sampled based on the way that we described our expectations. Our data seems to be matching those. So now let's go ahead and imagine that we've gotten a new set of data that came in. So time has gone by, collection of our data has continued, and now it's time to continue to use our model. So we'll use this second batch of data, and we'll put it through our data processing pipeline, and then we'll go ahead and apply the model. The same model that we just trained on the first batch of data. Now, in this case, of course, we're happy that we have some ground truth, and we're following our best practice here, and to look at how our model has performed on our new set of data. So again, we had that second batch. We took some of it aside, and we got some additional ground truth labels. We can observe that our score seems to have fallen pretty significantly. At this point, we could begin a process of debugging, but let's take advantage of great expectations first and look at what might have happened in our collection between the first batch and the second batch. To do that, we can just validate this new batch of data. Again, we'll do that using the same expectations we previously identified. In this case, we are observing that there are some differences. In particular, it looks like the expectation that we had for the distribution of genders and levels of education are different. Now, noting here that the age distribution is not different, seems to be the same. Let's go ahead and take a look at the gender. Well, in this case, we have exactly the opposite skewed distribution. In fact, there's way more men present in this data set than women. And that sort of population drift between our first collection and our second collection or batch of data is almost certainly what's driving our change in model performance. That's a way that great expectations can help to quickly zero in on problems in a pipeline and provide more information for data engineering and data science teams to be able to hone in on problems and quickly address them. Thanks for watching.